Welcome on Electrical Engineering 3. I was your voice all this time, but now I'm going to be a video, so we made some change. And so far we have discussed basically everything. We have explained how to draw your phase sequence, how does the three-phase system work, and then I said the phase sequence is a really important part of our three-phase calculation. So you need to go back and have a look on how to draw your phase sequence. Apart from that, we explained already how to deal with a delta load, because we said we have two types of configuration. We have a delta and a star load. But so far I've explained in the previous video how to do the calculation with a delta load, and you should be already mastering how to do those calculations when it comes to a delta load. Okay? But now, before we move to a star load, I want us first to have some look on the special case that we may have with a star load. Because with a star load is like a capricious child. So you need to take care of it. There may be some fault, and then every time we have a fault in the star load, it may affect our supplier. Okay? And then one of the first conditions that we are going to have is a short circuit load, which means on our video today we're going to discuss about a short circuit and as well an open circuit. What do we mean by a short circuit? If you go into your textbook that I have uploaded on the website, there is a question under exercise 2.1 which says impedance ZB is F. So every time in a problem when they state that a specific impedance is F fault or is short circuit, it simply means, like in this case, because they say ZAB was short circuit, was F fault. So this is what's going to happen to that impedance. Okay? But remember, we have what? We have a supplier, which is this side, and this is our del star configuration. But because our star is a special child, we are going to treat it specially. So we're going to have a look on a short circuit. You need to master it, and then you are going to master as well what your open circuit. Okay? But in the problem, as you can see, we were given a voltage EA, which is 220 at the angle of 18 volts. This is the reference voltage, and then the sequence was given as positive phase sequence. You're going to see all the solution under the memo that I'm going to upload today on the website on those two questions. But what I want you to master just now is for you to be able to solve any type of problem when you have a star load, a short circuit condition. How do you solve it? And it's really simple. So we're going to use different color just to show you that you don't really need to stress much about this, just need to master. So you draw your phase sequence according to the given information, and you know already what to do. Okay? So now, how do we solve our fault condition? As you can see, you have a current IA from the supplier. Okay? And this current is going in the junction. Can you see? Kirchhoff junction rule. So you have this current IA from the supplier is going into the junction. You have this current IC, which is going as well where? In the junction. Okay? But let's look here and see what's going to happen now. Can you see? We are on this junction here. Okay? If the current is coming on that junction, what's going to be the flow of the current? Remember from electrical engineering 2 or 1, we're talking about a short circuit condition. What does that mean? If I have a current that is coming to flow in a specific junction, down I have a wire, up I have a resistor. Okay? This current will choose the easy path where there is no resistance. Here we have 0 ohm, there you have 10 ohm. The current will choose the easy path and is going to ignore that resistance, which means that resistance is like it's not part of the circuit. So that's what happened. When our current IA is coming at this junction, it won't go down here because there is an impedance. It's gonna go where there is a least resistance way. Okay? And then the same is applied for the current C. Can you see? C, it won't go back to A, it's gonna come back down here because here down there is less resistance. Okay? So can you see? Now you have two directions of the current. And in this case, you have to choose one flow of the current, which means you have to choose the I potential of your circuit. And by what does that mean? It means you have a choice between the current I, A, which means the current is coming from, you see the red dot, from A to B, or C to B. Just make a choice. You have a choice between the two flow of the current. Okay? So I'm going to solve the two way of the current so they're gonna see how to, we are going to get the same answer. Okay? So look here. This flow of the current from A to B. How do we call it? We call it to be a current A to B. Can you see? A current that's moving from A to B. So it's going to be a current IAB. Okay? So when you come to do our calculation, we're going to say we have a current A to B. Okay? Which is going to be equal to how much? VAB over ZA. Because you can see that in this, we only have one impedance, which is ZA. Okay? And then we have another flow of the current, which is a current C to B. Can you see? C to B. So I'm going to come here and say another flow of the current, which is C to B. The current moving from C to B. So it's going to be voltage what? C to B over ZC. Can you see? So when you see that, it means that when you come to do calculation here, the given voltage is a phase voltage, you times it by √3. And then you go into your phase sequence, you take the angle of voltage AB, which is going to be a specific angle, and over that impedance. Okay? And then when it comes to the voltage VCB, remember, what did he say? When we only have 3 line voltage, we have what? 3 line voltage, which is the voltage AB, the voltage BC, and as well the voltage CA. Can you see that? Here we have voltage what? CB. Do we have CB here? We only have AB, we have BC, and then we have CA, which means we can change BC to CB. And in order to change BC to BC, we're going to come here. When you're doing our calculation, we take √3 times 220 because the given voltage is a phase voltage. You change it to a line, and then by the angle, you go into your phase sequence. First of all, you take the angle of BC. So you take the angle of the vector BC. And then you come here, you do what? Plus or minus 180. So that you can change it from BC to CB over that impedance. You're going to have a look on it in the memo that I'm going to send. Okay? So after getting these two currents that we said, but remember that in this impedance where there was a fault, we still have a current that is coming as well from the supplier, which is the current what? B. So we still have a current B, which is coming also from the supplier to the junction. Can you see? So we have a current B. Okay? So remember that on this junction you have 3 currents that are going in the same junction. So you are in the case where you have a current what? Current AB, okay, plus the current CB plus the current B, which all of them that are going in the junction will give us 0. Kirchhoff current law. Can you see? These currents are going in the same junction. The addition of the 3's will give us 0. Okay? and therefore our current B will be equal to minus AB minus ICB. So that's how you calculate any type of question when you have a fault condition. I will put a memo to this question, but what I want us to understand is just to see how to do this calculation. To identify that the given voltage that I have to calculate with, I have to add an angle of 180 according to the 3-line voltage that we always have in our problem. So I will expect some question. If everything is clear, which means no one will ask question. Okay? So if there is a question, it means it wasn't clear. Okay? And then in the next video, I'm going to talk about the open circuit.